Ever feel like your AI is thinking out loud for way too long? Well, what if we told you it doesn't have to? This paper flips the script on traditional LLM reasoning. Instead of forcing a model to think through long chains of thought, the authors try something bold. They skip the thinking entirely. They call it no thinking, a simple prompt trick that fakes a thinking box and jumps straight to the answer. The result? Models solve math, code, and logic problems faster, cheaper, and surprisingly well, especially when picking the best from a bunch of quick guesses. So, is all that thinking just fancy filler? Let's dive in.
Let's start with a question. Do large language models actually need to think out loud to solve reasoning tasks? You've probably seen the standard approach models generating long, step-by-step reasoning chains before spitting out an answer. It's like watching someone work through a math problem on a whiteboard, scribbling every intermediate step. This method, called thinking, is expensive. More tokens mean higher costs and slower responses. But here's the twist. What if we just skip the thinking part? That's exactly what this paper explores. The authors took a model, DeepSeek R1 Distill Qwen, and tried something radical. Instead of letting it generate a full reasoning trace, they fed it a prompt with a fake thinking block, like a placeholder that says, "Okay, I've finished thinking," and then forced the model to jump straight to the answer. They called this no thinking. And guess what? It worked really well. When given the same token budget, no thinking often outperformed traditional thinking across math problems, coding challenges, and even formal proofs. In some cases, the gap was huge, like scoring over 50% accuracy on a math dataset, while thinking only hit 29%, all using just 700 tokens. Even when scaling up with parallel sampling, no thinking kept winning, delivering lower latency and fewer tokens. So, the big idea here? Maybe all that verbose reasoning isn't as necessary as we thought. Sometimes, less thinking leads to better results. Now let's see how this plays out in practice. Take a look at Figure 1. Shows a side-by-side comparison of thinking versus no thinking on a math problem. The thinking model goes through this long, meandering chain of logic, backtracking, correcting itself. Classic show your work behavior. The no thinking version, it just says, "I've finished thinking," and drops a crisp, correct answer. No drama. This isn't a fluke. Across 7 benchmarks, check out Figure 2, no thinking consistently holds its own, or even outperforms thinking, when token counts are fixed, and the gap widens as you sample more answers. Meaning, no thinking scales better. Figure 3 drives this home. When you control for latency, no thinking still wins, delivering higher accuracy at the same speed. What's wild is that these models were trained to think step by step. Yet at test time, they don't seem to need it. Pair no thinking with best of n sampling or a verifier, and you get strong results, faster, cheaper, and often better. So, the lesson? Sometimes, the smartest move is to skip the monologue. To understand why this matters, let's zoom out. The field's been obsessed with 2 ways to boost reasoning: sequential scaling, long, detailed chains of thought, and parallel scaling, generate multiple answers, pick the best. Most work assumes explicit thinking is essential, that those step-by-step chains are non-negotiable. This paper flips that script. It shows you can ditch the reasoning trace entirely and still crush it. Just pre-fill a fake thinking block and let the model go straight to the answer. No fancy latent spaces, no routing tricks, just a simple prompt hack. And here's the efficiency win. Long reasoning chains are expensive. People have tried shortening them, but this method doesn't tweak the steps, it removes them entirely. The takeaway? In low-budget settings, skipping the thinking might be the most efficient hack of all. So how does this actually work? Let's break it down. Reasoning models usually structure their output with a thinking section, tagged with beginning of thinking and end of thinking, followed by the final answer. In the traditional thinking setup, the model fills that box with a full reasoning trace. No thinking? It's a cheeky workaround. Instead of letting the model think, you stuff the box with a generic message like, "Okay, I've finished thinking," and force it to jump to the solution. To keep comparisons fair, they use budget-forcing capping tokens, so both methods play by the same rules. The star model here is DeepSeek-R1 Distill-Qwen32B, a distilled version fine-tuned for structured reasoning. They also test Qwen32B Instruct as a baseline. The benchmarks? A mix of math, AIM-AMC, coding, live codebench, and formal proofs, MiniFi 2F ProofNet. It's a rigorous test, and no thinking aces it. Now let's get visual. Figure 4 gives a head-to-head comparison across all 7 datasets. You've got thinking, not thinking, and the QN baseline, all plotted by pass at K. The chance at least one of K samples is correct. Not thinking, in orange, isn't just keeping up. It's often ahead, especially as K grows. And it does this with way fewer tokens. Figure 5 levels the playing field further by enforcing the same token budget. Not thinking still shines, particularly when ESC greater than 1. Want better results? Sample a few answers and pick the best. Not thinking makes that strategy even stronger. The formula for pass at K is here too. It's just 1 minus the probability of missing all correct answers. Simple math, big implications. No thinking scales elegantly with sampling, giving you more bang for your compute buck. Let's talk efficiency. Figure 6 shows how thinking and no thinking stack up as you vary token usage. At low budgets, thinking sometimes edges ahead, see live code bench at pass at 1, but in almost every other scenario, no thinking catches up or surges past while using 2 to 5x fewer tokens. The hardest tasks, like Minify 2F and ProofNet, no thinking matches thinking's performance across all K, but with 3 to 4 times fewer tokens. For AIME and AMC, thinking might lead at K equals 1, but not thinking closes the gap fast as K grows. They even controlled for contamination by using a fresh AIME dataset. No overfitting here. The trend holds. Not thinking is lean, fast, and surprisingly effective. Tight on budget? This might be your go-to. Digging deeper, there's nuance. On AMC 2023, thinking and not thinking perform similarly. Maybe the model's hitting a ceiling, but on Minify 2F and ProofNet, not thinking gets shockingly close without any reasoning steps. Why does not thinking improve with sampling? Diversity. Table 1 measures entropy, how varied the answers are. Not thinking's outputs are more consistently diverse, which helps when you're picking the best of N. It's not just about being right once, it's about exploring broadly and selecting wisely. This sets up the next big idea. Not thinking's efficiency makes it a killer candidate for parallel test time methods. Speaking of parallel, let's talk speed. Figure 7 plots pass at 1 against latency for 4 setups. Thinking and not thinking, each with and without parallel scaling. Not thinking with parallel scaling wins. Higher accuracy, lower latency. Real-world applications? This is gold. How? Best of N selection. 2 ways. Confidence-based, using KL divergence to pick the surest answer, or majority voting, for exact match tasks. Latency is set by the slowest sample in a batch, and no thinking keeps it low while staying accurate. Now, how do you pick the best answer? Table 2 compares 3 methods: majority voting, confidence-based selection, and a hybrid. No thinking excels here too. On AMC 2023, it hits 85% pass at 1 with confidence-weighted voting, outperforming everything else. With perfect verifiers, like in logic tasks, no thinking plus parallel sampling matches or beats sequential thinking but faster. Without verifiers, confidence and diversity still carry it far. The takeaway: skip the verbose reasoning, sample smartly, and win. Wrapping up, no thinking holds its own even against full-blown thinking. On AMC 2023 and Olympiad Bench, it outperforms, especially with parallel scaling, cutting latency by up to 9x. The exception? Live Code Bench, where exact match voting falters. But overall, the message is clear. Elaborate reasoning chains aren't always needed. No thinking is lean, fast, and scalable, perfect for real-world efficiency. Final thought? Maybe the smartest models don't need to think aloud. Sometimes, the best answer is the one that skips the monologue. Thanks for joining us today. Happy exploring!